guys, welcome to a new video about DSP design on FPGA. Today's video is going to be about the design of a dual channel FIR filter. In the past video we talked about how to design a single channel FIR filter. We designed that on System Generator and we simulated it, and once we were happy with it we packaged it and we sent it to Vivado for validation, and indeed we did our validation in both time domain and frequency domain, and we validated the design specifications of the filter. Today, the reason for today's video actually is that this DSP block, which is the dual FIR filter, is going to be used in an FM radio receiver. So we want to take an FM modulated signal and we want to mix it with an LO and then run the INQ through this filter and then get the baseband, which is the FM baseband signal, and then we take it for the modulation. So if you are following this series, at the end of this series we're going to implement an FM radio receiver, and this tutorial today is for one of the very important DSP blocks in the toolchain for this FM receiver. So if you are interested, please stick around till the end of this video. Okay, let's get started. So first thing you need to do, you open your System Generator workspace, and then as usual you would go to the Simulink library, and from the Simulink library you get the token. So the token, you can find it inside the Xilinx basic elements, I believe. Let's see what's in here. Yeah, this is this one. You click on this one, System Generator, and you take it to your workspace, and in there I'm just repeating what I did last time. So most of the information at this point were covered in the previous tutorial. So when you click on it, it opens up. So setup, you select your FPGA part number, so this is what I have, and then where you want the IP to be packaged to. For here I put the link to where I want my IP, my System Generator IP to be packaged, and the name for it, and then the clock in here that I selected 200 megahertz. So the period of the clock of the FPGA is 5 nanosecond, and everything is default. I did not touch anything else there. So that was it for the System Generator token. Then you'd need to get the FIR compiler 7.2, and this is the one I'm talking about right here. So same thing, you get it from the browser, from the library, and then you need to get this FDA tool as well from the same library. So the FIR today that I want to design has a sampling frequency of 10 megahertz. It has a cutoff frequency of 100 kilohertz and stop band of 300 kilohertz, and it has a rejection noise of minus 60 dB, and I have a ripple of 0.2 dB. And once we select the design specifications of this filter, we click on design filter, and the tool will generate the coefficients for us. In this case it turned out to be 125. Yeah, and then you select which filter you want. So in this case I just selected a common filter, which is equiripple filter, FIR filter. So the coefficients, if you need to look them up, so they are here. So you click on this icon here and they come up here, and here you have two options. Either you export them into your workspace by clicking on export here, and then workspace, and you hit export, and you can name them, give them a variable name, and you will see them in your workspace. Sometimes you need that so that you can scale them up or do some processing with them beforehand. Anyways, so this is the first option. Second option, you can save them as a file, and then you can process the file later for some other reasons. Let's say you want to change the gain of the filter or whatever, so you can save them as a file and then process them in an Excel file if you want for a specific gain that you are interested in. So same thing, you select this and then you hit export, and it's going to ask you where you want them to be saved, and you do all that stuff, and that would be it. So anyways, up this point we are done. So the tool generated the filters for us for the filter we want, and we can just close this window. Now the configuration of the FIR compiler, it's nothing different than what I did last time, except this time I have a decimation of 10. Why 10? Because I want the output data to be at 1 megahertz. However, for the case when we implement the FM radio, it's not gonna be 1 megahertz output data, so I would probably go lower than that. So we'll see how it goes. So this is in terms of decimation. Here I selected input sample period, and later I will show you I also could have selected the hardware oversampling rate, but let's talk about first about the input sample rate. So the input sample rate is selected to be 1. We have 2 paths that run in parallel, one for the I, one for the Q, and the number of channels is just 1 channel here. So it's not multi-channel, this filter, it's just 2 paths in parallel with a single channel. The implementation. So the implementation, I chose to have quantize only, coefficients with 18 bits, and I went for best precision for the fraction length, and I want my output width to be 18 bits. Could be 16 bits, but anyways. That's it. And then these detailed implementation, you don't touch anything here. The interface, same thing, you don't touch anything here. So these T-lasts, TUs are used usually for multi-channel, more than 2 channels, and this advanced you leave it the way it is. So the configuration at this point of the FIR compiler is complete. Now let's talk about the input first. So we have input channel 0, we have input channel 1. What I'm doing here, for the sake of simulation, I'm giving here a signal. I call it sine. Both of them are sine. I'm not doing quadrature here. This is just for the sake of demonstration. However, later on in my code, I'm going to be using a quadrature input. I'm going to be using an I and Q. I'm going to be using a sine and a cosine of an AC sweep. And we will look at the frequency response, hopefully, if I have time, but I can promise I'll be looking at the frequency the time domain response of the input. So for the sake of demonstrations, I chose this signal to be, let's see here, what do we have? I have here 10 kilohertz, so it's supposed to pass easily through the filter, and I have here 150 kilohertz. So 150 kilohertz certainly will be attenuated by a certain amount, and we will notice that, and we're going to increase this into 300 kilohertz and see if anything will even pass. So that's pretty straightforward, nothing special here. So this gateway in, you need it because it acts like as an ADC, so it's used for sampling. So I set the sampling frequency for this to 10 megahertz because that's how that are going to be coming into the FIR. So there will be an ADC, and I have that ADC. I talked to you guys about it last time. It's an ADC 1173. That's the part number for it, and its sampling frequency is 10 megahertz. I selected here rounding to minimize the rounding, the truncation and the error. So rounding here seems to work pretty well, at least for me at this point. And then for the overflow, I selected saturated. So I'm mimicking here, as I said, an ADC component. So it's 8 bits and has 7 bits fractional, and it's 2's complements plus or minus. Okay, so that's what I did. This for the gateway in. Same thing happens here. The interesting part I want to tell you guys here is this: how do you control the data valid here? So the data valid here, my intention here is to have only 1 pulse per valid data. So basically I want 1 pulse to keep coming at a rate of 10 megahertz. So how do you do that? Here I put these components from the Xilinx components. So same thing, they are taken here from the library browser, so you'll find them there. So this is just a constant, and I set that to 19. Why 19? Because I want to have a counter that counts all the way up from 0 to 19 and when it's equal 19, I want to generate a pulse, single what do you call, single one clock cycle pulse, which is it's not 5 nanosecond, but less than 5, just less than 5 nanosecond pulse. So we have a counter here that counts from 0 to 19, and it steps by 1, and 19 is 5 bits is enough, and this is the sampling frequency. Actually, it is 5 nanosecond, yes. So we want a pulse for 5 nanosecond so that the FIR can sample the inputs data. So basically your counter is counting, so, and then when it's equal 19, a pulse will be generated, and this way we will be clocking our data correctly into the FIR. So that's pretty much it. And here, this is the output, this is the gateway out. These are just used to check the output of the filter, how it looks like. We have 140 already, so this one is always high. And we have T valid, so this T valid will be high whenever there's a sample coming out, processed inside the FIR and come out. It will generate a pulse. So the pulse I expect over here, I expect a pulse every 0.1 microseconds. So the rate here is going to be 10 megahertz, and the input here is going to be, I'm confused here, sorry guys. So the input is going to be, we are sampling at 10 megahertz, and the output is going to be 1 megahertz. So we're supposed to see a pulse every 1 microsecond. Okay, so what else? I think that should be it. So let's run the simulation here and see what's happening here. So we have 10 kilohertz here, and we have here 250, I believe, or 150. Let's see what we have here. We have 150 kilohertz. So let's see what's going to happen here. Let's turn this on. So it's running. There you go. So you can see now. So the top one is 10 kilohertz, and the bottom one is 150 kilohertz. So what do you guys see here? You see that the amplitude is not quite 1, is less than 1. So the signal started to get attenuated, or got attenuated way before then, at 100 kilohertz as it's supposed to. And you can see in the plot below for the 150 kilohertz, you can see we have less components, and this is because of frequency is high. So the top one is 10 kilohertz, and the bottom one is 150 kilohertz. So it's 15 times faster than the top, than 10 kilohertz. So that's why we have less samples per period for the second plot. That's why it looks like that. Now let's change that, and let's go and change 150 to 300. So technically at 300 I'm not supposed to see anything. I'm supposed to see basically nothing, because the input is supposed to be attenuated severely. So let's do that. Let's write here 300. Apply. Okay. Actually, yeah, that's okay. Can hit save here. And then let's run it. So it's running again. So let's see what's going to happen here. Exactly. So indeed, so nothing is coming out over here, because we're at the stop band right there, and the first frequency is coming out. Okay, you can stop this. Few verifications over here. So I told you guys here that the pulse is supposed to be coming at 10 megahertz, correct? So let's validate that, because there's a pulse here. We'll have to look at it. So that's how it is. So exactly, so we can count how much distance we have from here to here. So this one is 0.001 times 10 to negative 6 to negative 4, sorry, as you can see here. So this indeed 10 megahertz. So let's look at the data output, because we expect the data output to be at 1 megahertz rate. So let's see if that's the case. So same thing, these are the pulses. So let's zoom in more. So it's kind of hard here to see it, but anyways, if you measure here, there is a distance of about 0.01 times 10 to the negative 4 between this and this, and that should be 1 microsecond, which is 1 megahertz. 0.01, and the other one was 0.001. Can't recall that. Let's just make sure here. Let's do this original. So it's here. So it's 0.001 times 10 to the negative 4. That's indeed what we expected. So that's pretty much it in terms of the the simulation here. So let's say we are happy with our design and we need to package this and send it to Vivado so that we can deploy it onto the FPGA. So the next step is pretty easy. You go back again to the system generator, you open this token over here, and then you select already your, let's say, your FPGA part number and everything, and keep everything here the same, except here you browse to where you want this IP to be packaged. Basically, like in my case, I have my USB drive here. I created a directory or a folder called dual channel FIR IP, and I pointed to it, and you're gonna hit apply and then generate, and it's gonna take, I don't know, depends on how fast is your computer. It might take about 5 minutes, 3 minutes, and once it's done, it's gonna tells you that the generation has been completed, and you're gonna get a timing analysis report that if you pass the timing, if your design passed the timing, it will tell you. If not, it will tell you it did not pass the timing requirements, and it tells you where and why, setup time or hold time, and which path. So I cancel this, and that's it. And then when you go to your Vivado, I will show you how we'll do that in your Vivado, how to get the IP. Okay, let's now talk about the other configuration I want to tell you about, which is the oversampling. For the case of the oversampling, if you guys see with me here, we have a clock of 200 kilohertz, and we want to sample at 10 kilohertz. So the ratio between the two clocks is 20, right? So what you need to do, you need to come over here. I'm not talking about this image here. This image here, you can keep it. It has nothing to do with that. So you're gonna come over here, and instead of input sample period, you're gonna be selecting hardware sample rates. And here, just a second, let's see what's going on here. We have to pause this before we do any changes. So let's pause that. Let's pause it. Now we open again, and then we go back here to channel specifications, and here you select hardware sample rates, and here you select 20 like this, and you don't do anything else, and then you close this, apply, and then okay, and you are done. Now you can see things changed. Now we don't have T-valid at all. Now T-valid is gone, and then you're gonna take your I, which is channel 1, you give it to path 1, and channel 2 you give it to, like in this case, you give it to path 0, and you package your IP as we did before. This stuff you don't need to delete it. You don't need this stuff, and you package your IP and you send it to the Vivado for deployment onto the FPGA. So that's pretty much it in terms of system generator. So now let's go and take a look at the code, look at the IP that we packaged, how we did it, and look a little bit at the code. In this first part, I'm not gonna be talking much about the code, but in the second part, I'll be talking more about the code. I will be doing a live demo about the time domain response in time domain for the response of the filter, and I will be doing be running the ILA, which is previously called ChipScope live, and we can look at how the filter is performing. We'll have an AC sweep for the I and Q, and we were looking at the output of the filter, how the outputs respond to different frequencies at the input level. Okay, so now let's go to Vivado and take a quick peek at the code. So the first thing I want to say here is that if you need to get the, because you packaged your IP and system generator and you saved it in a folder somewhere in your work directory or your USB or whatever, and you want to bring that back to your Vivado for implementation. So what you need to do, you need to come to your hierarchy over here, and then you go to this plus sign here, and then you say you want to add or create design sources, and you go here next, and you go here add, and add file. And you want to come to this folder over here. You want to come to, like, I have my USB drive, so this is the location where I put it, and you go to IP, and here this is the name of the IP. Okay, and here you have just remember the extension XCI, so this is what you need. So you can rename it if you want, and you hit OK, and once you hit OK, your IP will be added into your IP sources, and this is the IP we have. It is here, and if you double click on it, it's going to open up. And then you can see we have the coefficients, we have all the stuff we need over here. So sometimes even if you package your IP and everything and you need to edit it, change something, this option gives you the capability of changing any of the parameters that you selected before. So for example, you can change your decimation, like you have 10, you can change it to 20. So all that kind of stuff, you can, anything that you can edit, you can do it here. Quantization only, you can change to something else. So this is one of the good things about this. The other option, if you want not to do it this way, this happens only if you export the IP as an .xci. The other option is that you come to your IP catalog over here, double click on it, it will open up, takes 1 minute or two, and then actually what you need to do, you need to come here and you hit IP settings, and you hit on add. So here when you add, click on add, it takes you to where you want, you point to where the IP is saved, like in this case is here, and you click on IP here like this, and you hit select, and it gets selected. So in my case I did that already, and that's why it is here for me already. This option has something that limits you from changing the components inside. For example, so this is the one here. If you open it, it just gives you like this, and you cannot change anything here. So it is as it is. It's not, you cannot edit it. It's just as it is. Whatever you have on your system generators will be transferred as an IP like this, and you cannot edit it. However, if you transfer it as a .xci, you'll be able to edit it. So this is how you transfer your IP into your Vivado. Now we look at the code quickly. I don't want to spend too much time on this. So the top level, I don't have much here in the top level basically. So you have I have a PLL. This one I just generated my clocks. I have 10 megahertz input clock on the FPGA, and I want to generate 200 kilohertz. I did that to generate that. I have an ILA over here. I did that just for demonstrations for the next part, and I have a DDC sweep. So my DDC sweep here, basically what it does, I talked about DDC before, by the way. I'm doing here a sweep from 100 from 100 kilohertz, from 100 hertz, sorry, all the way to 500 kilohertz. So I have steps, like each step is 100 hertz, so that's why I have about 5,000 steps, and I have a dwell time of 10 millisecond per frequency. So I talked about that last time, so the code is also on my GitHub, so you can take a look again and see how it is. So there's nothing new over here. So basically this module here is just to generate the basically the phase counter for that we can feed into the DDS to give us the frequencies of interest. So that's pretty much it. So the output of this module here goes to the DDS IP core. So I show you what I mean here. The DDS IP core takes 32 bits, which is the phase increments, and it generates the frequency of interest for us. So for me here, I just want to go very simple. I just use only one IP core to generate both the sine and the cosine, and both the sine and the cosine are 8 bits, and I selected the stream in here instead of fixed frequency. That's pretty much it. And also to get things going, so because I want to look at the outputs of the filter, how it looks like in real life on my oscilloscope. So the data will be sent to a DAC. So I have a DAC over here. DAC also has been covered in the previous tutorials. There's nothing special here. Basically DAC is also running at 200 megahertz. This is just the clock, but the sampling is dependent on the FIR data out. So whenever the FIR have some data out ready for us, we take that data and we send it to the DAC, and that's how I'm doing it. There is 2 control signals for the DAC. These are the ones you set them initially to 0, and you load your data. So the data is supposed to be 12 bits, so the DAC is 12 bits. So the output of the filter is 48 bits, so each channel is 24 bits. So keep in mind there is fractional bits that are less effective, and that's how I came up with these numbers from 15 to 5, and then bit 23 over here is a sine extension bit, and bit 47 here is a sine extension bit as well. So we will look in the next video, should be coming up in 1 day or 2, how this code performs, and in the meantime we will confirm the performance of our filter. So this is it for this video. I hope you guys learned something from it, and stick around. In the next day or 2 I will release part 2 of this video. It's gonna be in the form of a live demo that demonstrates the performance, that confirm or validate, I would say, the performance of this FIR filter. Until then, take care of yourself, and good luck. Bye bye.